In this class, we're going to consider power series. And you can think of this as just being an introduction to the topic of power series. So we're not going to get into too much detail in this class, nothing too technical. We're just really going to present an overview of what power series are, and then we're going to expand upon that in the classes that follow this one. So a power series is particularly useful because we can use these forms, these power series forms, to represent functions, and then we can do various things with those functions in their power series form. And we're going to look at two forms in particular, a Taylor series and a Maclaurin series, and we'll look at those in the classes that follow this one throughout this series of videos. So first of all though, just backtracking to get the overview, what is a power series? Well, a power series is an infinite series where we've got ascending powers of the variable, the x term usually. So the general form of a power series is an infinite sum, so we're going to sum n equals 0 to infinity, some coefficient term, which we're just going to call a sub n, and then we've got x minus either a or c. I'm going to write this with a c, although you'll see that written with an a sometimes as well. Importantly though, to the power of n. So if you consider this form, what is going on here? Well, every time you take another n value and put it here in the power, you're going to be generating another power on the x term. So you're going to get an x to the 0, which is just 1. You're going to get x to the 1, which is just x. You're going to get x squared, x cubed, etc. So that's why we call these a power series, because you're getting that ascending powers of the variable. Note that the a sub n term is not related to the x. So a sub n is independent of the x, but you can think of a sub n as being some function of n, and we'll consider as we go through the classes in this series different forms of that a sub n term. When we get to Maclaurin series and Taylor series, that a sub n term, that coefficient term, is going to be generated by taking subsequent derivatives of the original function. But that's for the future. So just for now, let's consider this form. If we start expanding this out, so subbing in our various n values, we're going to get our first term of a sub 0. We're then going to have x minus c to the power of 0, but anything to the power of 0 is just 1, so that term effectively disappears. So your leading term in this expansion is just this constant term. Then when we get our n value to 1, we're going to get a sub 1 x minus c to the power of 1, or just x minus c would be fine. And I think you get the idea. When n is 2, we're going to get our coefficient a sub 2, and then we're going to get x minus c squared, and that's just going to carry on like that forever. So a couple of things that we want to highlight at this point about these. So the first thing is what I mentioned already, that a sub n is unrelated to x, and in fact a sub n is going to be some function of the variable n, okay, so the placeholder n. So a sub n equals some function of n. There are going to be different forms of how that a sub n term is generated, and that's a big part of working with power series. We're going to see that in the classes that follow this one. You're going to learn some particular forms for this f of n function. The other thing I want to highlight is that what is the c value? Well, the c value, which is an x value, and the c value is the center of the power series, okay? So it's where it's kind of anchored, it's where it's centered, where it's sort of focused on. When we get to looking at Taylor and Maclaurin series later on, the center is going to become quite an important thing, okay? But we'll just park the idea there for the moment. Sometimes the center value, the c value, equals 0, in which case when c is 0 you get a more simple form of the general power series, because the c value here disappears and you're just going to get a sub n, the coefficient term, and then x to the power of n. So the first form, these centers where they're non-zero, a non-zero center, they are associated with Taylor series, which we'll look at later on, and these centered at 0 infinite series, these power series, are associated with Maclaurin series, which we'll look at later on as well. So Taylor series, Maclaurin series, that's really the direction that we're going in with these power series. And they're similar, but just the fact that the center is 0 in this more simple form here. So what would be an example of a power series? Well, let's actually take the example of a Maclaurin series. At this point, you don't need to know about what a Maclaurin series is. This is just chucking that out there as an example. So this is going to be the Maclaurin series for the function f of x equals e to the x. So that's a function that I'm sure you're already very familiar with. So the exponential function. You've probably used that in a bunch of ways many times in the past, but you've probably never, if you've never seen this material before, considered that it could be written as an infinite series. When you write this as an infinite series, it comes out to be, I'm just going to put this again over here, it comes out to be that e to the x can be written as the infinite series, so n equals 0 to infinity, so the power series form. And it's a really neat form, I really like this one. It's just x to the power of n over n factorial. So what does that mean? Well, that means that if you start putting in your n values, you're going to get, well, basically you get a 1 for the first term, then you get an x to the 1, which is just an x, and then you get an x squared over 2 factorial, and you're going to add to that an x cubed over 3 factorial, and that just carries on indefinitely like that. And basically, this power series represents exactly that function. Now, we're going to talk later on about what x values a power series is valid for. They're not always valid for all x values. We've got a thing called the radius and the interval of convergence, which basically tells you for how many x values the series is valid for. For some functions, they're valid for all x values. For other functions, they're valid for only a certain set of x values. So the functions represented by the power series, sometimes only on an interval. Outside that interval, they're not related. The two are unrelated, or they don't exactly represent each other. But some functions have got a valid power series expansion for all values of x. So in other words, for that case, these are exactly the same thing. This represents perfectly the function. But we're going to get into all of that in more detail in the classes that follow this one. So again, that's really just an overview of what power series are, and it just sets the direction for where we're going, which is particularly to look at Maclaurin series and Taylor series, and then some of the applications of those. Why might we want to represent a function as a power series? What can we do with that that we can't do with another form? So I hope that little overview is going to be useful, and if you're ready, you can just move straight into the next class, where we're just going to start to dive a little deeper into this material.